Hi, this is Darren with the Mississippi State Chemical Laboratory, and today we are going to be doing our lime analysis. Now you may be wondering, what is this and why doesn't it look like a small green fruit? And that's because these are not the limes that you see in the grocery store. This is ground up limestone and other nutrients. Farmers use this to raise the pH of their soil so that it doesn't get too acidic. It's mostly made out of limestone, like I said, and so one of the analyses that we do is CCE, which stands for calcium carbonate equivalent. What we're basically doing is checking to see roughly how much calcium carbonate is in there, or ingredients that will act like calcium carbonate when put into soil. The other thing we do for this is called relative neutralizing value, and that's related to the CCE, but it takes a little bit of extra calculation to get there. We have to use the balance to measure out our masses to start this analysis, but before that, we're going to have to make sure our balance is calibrated. So we want to do this every day that we use the balance, and just good practice is you want to check the balance in roughly the same mass range that you're going to be measuring. So we're going to be measuring about 1 gram of each of these lime samples, so I'm going to be using the 1 gram and the 2 gram reference weights. So we have our record book here. You can turn to the most recent unused page. Put down our date, 5/28/20. Standard use is WW06. Alright, and then the actual weight that we're going to be using is our 1 gram weight and our 2 gram weight. Get these out. You don't want to touch these with ungloved hands, sort of same as a cuvette. You can get oil on them and then that will change their mass. This balance has a nice little button that automatically opens the shield. So we can grab that, put it on there, close the shield, and wait for it to stabilize. We typically see with these weights on this balance, it comes in at about 0.0001 or 0.0002 above where it's supposed to be. Looks to me like it's stabilizing at 1.0001, so the difference is 0.0001. And I can give my initial on that. And then now the 2 gram measure. All right, that looks pretty stable at 2.0001. Giving us a difference of 0.0001. I initial it, and I am just about ready to measure my lime samples. Just going to put these reference weights away, and we just keep them right here by the balance. Okay, so now I am ready to begin measuring out the masses on these samples. One sort of peculiar thing about this analysis is instead of just measuring something out and writing it down and taking that into account with the calculations later, the way that we have this set up is we must measure between 1.0000 and 1.0020 grams. So basically 1 gram plus 2 milligrams at most. And I think that's just sort of an artifact of the spreadsheet we use, making it easier to handle the calculations. You typically don't want to do that in just terms of good sampling practice. However, it's sort of okay with these lime samples because they are so homogeneous to begin with. So we are probably not going to be introducing any sort of sampling error by going for our exact mass of 1.0000 grams. So to start, I have my labeled beakers. I have 11 samples to measure today. I'm not going to show you all 11 because that would get pretty tedious. But I have 250 milliliter beakers for each of the samples, and they are labeled according to our LIMS system, so I can keep track of them. So I put the boat on the balance, let that stabilize for a bit, zero it out, and then I'm ready to start measuring. With a clean spatula, you just want to grab, you know, about a gram. And this can take some time because we have to be so exact with it. When we get toward the end, we're going to have to, you know, add teeny little bits or take teeny little bits off. And again, that is sort of goes against good sampling practices, but it's okay in this case. So right now it's reading about 1.0037, so we still need to take off a little bit, but when it gets down to this much, you can see just how how much a tiny little speck makes a difference. And again, I want it to be between 1.0000 and 1.0020. I am there for this one. So even though we don't take the number into account in the calculations, I like to write it down just to know, so I can look back in case anything looks weird. So that's, I'm going to call 1.0010. And get that out and put it in the beaker. If we were going to be doing this, so eventually we're going to be doing a titration. And if we were going to be doing this colorimetrically, we would probably want this in Erlenmeyer flasks. In fact, that's how we used to do this analysis, was in an Erlenmeyer flask. However, we've transitioned over to being able to do this analysis via a pH meter. And so just in order to get the pH probe in and everything circulating well, it's just a lot easier with a beaker. That does provide a couple of extra challenges, which we'll see later. It makes it a little bit, you have to be a little bit more careful during the boiling step, and you have to be a little bit more careful during the titration just not to spill anything. But otherwise, it makes it a little bit easier, especially some of these samples, like this one's pretty light colored. You would be able to see the phenolphthalein turn from pink to clear or clear to pink through the solution that's going to make. But some of the samples can be pretty dark, and it makes the colorimetric titration, I would say, less accurate because you can't see the endpoint quite as easily. So I'll do one more of these on camera, and then the remaining 9 I'm just going to save for off camera. So again, put the boat on the balance, zero it out, it up. Sample. I'm going to clean off my spatula in between. Shouldn't make that much of a difference, but there's no reason not to. I will probably call that at 1.0004. Okay. Put this out, put it into our beaker. When I put this in here, I do a little bit of a tap to make sure I get as much of it in there as possible. You know, we're going to be doing a titration, so we want to make sure our masses are accurate. If you ever see anything like coated on the inside of that, then you may have to take a small brush to brush it down into the beaker. But I'll say that's it for now. You can use your imagination for the remaining 9. It'll look the same as the first 2. So I've got all of the beakers filled with 1 gram for each sample. The next step here is just to add about 50 milliliters of deionized water to each beaker. This measurement does not have to be exact. It's not going to affect our results one way or the other if we are a little bit low or a little bit high. So I'm just going to pretty quickly use a graduated cylinder for each of these. You do want to make sure that you're using deionized water. If your water is, you know, a little bit too acidic or a little bit too basic, that would affect your results. Not by much, but enough that it would matter. So we have our deionized water station over here by the water bath, and we can just use this same graduated cylinder for each sample. Again, I probably don't have to do all 11 of these on camera. This is a lot quicker than weighing stuff out on a balance, but I might cut this after another couple, because I don't have much more to say about it. I'm filling up beakers with water. You can see in that last one, and maybe in this next one, how opaque the solution gets when you mix the lime or the marl into water. And you can see why that would maybe be difficult to do a colorimetric titration with. This one, maybe not so bad. It's still fairly light colored, so you'd be able to see the pink phenolphthalein coming through, but not as easily as in a clear solution. And it certainly does get darker and more opaque than this. Anyway, the next part is going to be the digest, so we'll skip ahead to that. So this will be our first training video that takes us outside of the inorganics laboratory. This is our titration station set up over in G014. It has basically everything we need to do our lime titration. You've got the pH meter over on the left. It's a little bit simpler than the one that we use in the inorganics laboratory. We have our buret on the right, and behind that is our hydrochloric acid solution that we're going to use to digest. So a lot like the bicarbonate titration from the previous video, this is a back titration where what we're going to do first is, you know, we measure out our 1 gram of lime or marl. Then we're going to add in 50 milliliters of standardized hydrochloric acid solution, and that's going to react all of the limestone, all of the calcium carbonate in that sample, and there's going to be some of that hydrochloric acid left over. And then what we're going to do after that is titrate the hydrochloric acid with sodium hydroxide, measure how much of that titrates, and then we can know how much hydrochloric acid we have left. We can take from that, calculate how much we used, and then go and calculate how much calcium carbonate or equivalent there is in the sample. So this part's pretty simple. Just going to take each sample and add in 50 milliliters of the hydrochloric acid solution. I used to do this using this big volumetric pipette, but we now have this
50 ml dispenser, which is nice. Whenever you use one of these dispensers, you always want to give it a couple of primes to make sure you get any air bubbles out of the system. I'll give it maybe one more. And then uncap it, set the flow. And for this one, I like to go fairly slowly just to, we're delivering a lot of volume and you don't want to splash too much. For some of these samples, you'll be able to see it start reacting right away. You'll see bubbles forming. That would be the carbonate breaking down and forming carbon dioxide. You might be able to see some foam on that one. You can see the bubbles coming out. What we're eventually going to do is put these on a hot plate and boil them just to really make sure this reaction goes to completion. So actually, as I'm filming this, I'm noticing that we're getting some air bubbles up in here. So I think that was the last one that we can safely do. Just because the level of hydrochloric acid in here is getting too low. So I'm going to cut it now, refill this, and keep going. Okay, got that refilled with more standardized hydrochloric acid solution. And that brings up sort of a side lesson. Always pay attention to what's going on, because if I hadn't really been watching, I wouldn't have noticed those bubbles getting up into there, and I wouldn't have dispensed exactly 50 milliliters, which is what we would need, and then that whole titration I would have had to start over from the beginning. So now that I've put it in there, I'm going to prime it again. You can see the air bubbles in there that we're going to try and get out. Okay. And I'll do a couple more of these on camera, but as with most of this, there's 11 of them, so you don't need to see them all. Just raising slowly, pumping down slowly. Ooh, that's a fizzy sample. Another side lesson, take the time to appreciate the fun things that go on in the chemistry lab. Anyway, I'm going to finish all the rest of these off camera, and then we'll go on to the next step, which is going to be the boiling. So before we get these boiling, I'm going to want to add some boiling stones. This is just going to make the boiling less violent so that we reduce the risk of anything boiling over and us losing some of our sample. There's not really a set amount that you need to put in. I usually just get myself a little handful and then put a few pinches into each sample. You really don't need any more than, I'll say, 5 to 10 stones per beaker. Okay, and then once we got those, we can put them on our hot plates. We have 2 hot plates set up in our fume hood over here. I like to set these to 450 degrees for this. Should be able to see on the display that temperature. This exact temperature doesn't matter that much. You just want to get the stuff boiling fairly quickly. And then once it is boiling, we want to boil for 5 minutes. Sort of the unfortunate thing about having 11 samples right now is we can really only fit 8 of these on at a time. And so I'm going to have to do 2 batches. But I'll start with 8 and then do the remaining 3 afterward. I don't think I'll film this entire process because it takes a few minutes for them to start boiling, and then they spend 5 minutes boiling before we take them off. But you can imagine sitting here watching some beakers. I'll cut to when the action starts. Okay, so it's probably been about 15 or 20 minutes. Finally, all of the beakers are boiling now. I had to turn the right hot plate up to 540. It just seemed like it was not getting hot enough to go. So the samples on the left hot plate have been boiling for a bit longer, but that's okay. The protocol is at least 5 minutes of boiling, so you can go a little bit over, and that it's totally fine. The main point is that you just want for that reaction of hydrochloric acid and calcium carbonate to go to completion, and so doing a little bit more boiling isn't going to ruin anything. You don't want to get this boiling and then take off for lunch or anything, because then you may boil all of the water away. But 5, 10, 15 minutes of boiling is fine, just minimum 5. So at this point I would say, hey Google, set a timer for 5 minutes, and then my phone would say, sure, 5 minutes, starting now. And then we would sit here and wait for the 5 minutes, but we're not going to do that on camera, so I will see you when the 5 minutes is over. Okay, our 5-minute alarm has gone off, so now is the time to remove these from the heat. Remember, they are boiling hot, so I like to use just a wadded up paper towel. You can use gloves, like big thick gloves if you'd like. Make sure you turn these off. And then we're going to let those cool in the hood for about 30 minutes. You just want to make sure they're roughly room temperature when we go to analyze them. Now is a good time actually for us to go over and calibrate the pH meter, because we're going to be using the pH meter for our titration analysis. So here we have the pH meter that's over in the feed and fertilizer lab. It's a little bit simpler than the one we have in the inorganics lab, but it works on the same principle, and we have to do the same thing with it, which to start is our calibration. Now I'm not going to go as in-depth into it on this video, because there's a whole other video on calibrating and using the pH meter. You can check back for that. Maybe I'll put a link in the description. So I'm just going to very quickly go through. Have to turn it on. We have it in the storage solution, so I'm going to rinse off the probe with deionized water. And then start the calibration. And the one main difference between calibrating this instrument and the other instrument is that this one has just set pH values that it calibrates to. So instead of telling it I'm putting in a 4, a 7, or a 10, it will take whatever it's closest to and assume a 4, a 7, and a 10. So we will start with our pH 4 buffer.
I'm going to hit the calibrate button. Alright, and then you can see it went from 4.13 to 4.00. That's saying, okay, we have this calibrated as our first point. Bring the 7 over, but make sure to rinse the pH probe in between. Got our pH 7 buffer. Let's put it in and hit calibrate again. it to 7.01. Put that away. So in a lot of ways, this is actually an easier instrument to use, and so if you wanted to get started on pH, this one's maybe a better place to start, just by a little bit. But it's a little bit more automated and makes a few assumptions that the other one doesn't. So I'll bring in my pH 10, hit calibrate. Alright, now that calibrated 10.04. Gonna rinse it off, and then finally, just like with our other pH meter, we're gonna check that calibration now with a 7.4 buffer, and we're hoping for it to be in between 7.3 and 7.5. And I find that this pH meter actually usually comes very close to 7.4. So we'll see if it happens. Just put it in there and watch the reading. You can see it going down. It's at 7.5 right now. I don't know if you can see on the screen, but the little decimal point is flashing, so that's saying it's still equilibrating. And then once that goes solid, that's when you know that it's giving you an official reading. Okay, so 7.45, that is within our tolerance. So this pH meter is calibrated for today, and we can get back to our titration.
Alright, so we are ready to begin our titration. This is going to be a sodium hydroxide titration into hydrochloric acid. So I have our 0.25 normal sodium hydroxide here, and I've got this buret, famously difficult to film because it is so tall. But I'm going to fill it up to the top and do the same. Probably not going to go into as much detail on exactly how to do this because in the carbonates and bicarbonates video I have a lot of detail on titrating with the buret. So let's fill this. Getting close to the top. Okay. Take that off for now. Then I actually want to come down and look at the bottom. Again, there will be an air bubble in this area that we want to get rid of. So just going to let some sodium hydroxide flow through and make sure that there are no air bubbles trapped in that area. That looks pretty good. Now, of course, we need to go back up to the top, refill up here. Okay, and then perhaps the most important part is getting it to the line that we want. On this buret, you can see the 0 line is right about there. So I'm going to slowly drip down from the bottom. You can't see me doing this, but this is the more important part to be watching until the bottom of that meniscus, that curvy part of the liquid, is touching that 0 spot. Okay, so now we are ready to titrate. So now we're ready with our first sample. We want to rinse off our pH probe because it was just in the storage solution. Just give that a good deionized water rinse. And then we will put it right into our sample. So this won't necessarily change on its own. If it's been locked in place for a while, it won't think to read, so you have to hit the read button to get it to read. You can see it's at a very low pH. If you recall, we started with calcium carbonate, we added a bunch of hydrochloric acid in excess and reacted all of the calcium carbonate, and so we had some hydrochloric acid left over, so that's why we're at such a low pH. We're going to titrate it with sodium hydroxide, and we're shooting for a pH of 7. One of the benefits of doing this via a pH meter is that we can go kind of fast for the first part because it takes a while to get up from the very low pHs. I would say you can go pretty fast watching this until it gets to about 3. When it gets to 3, you'll want to slow down the flow of your buret quite a bit, and then once it gets to 5, you'll basically want to stop and go dropwise, because those last 2 pH between 5 and 7 go very quickly. But for now, we can just let this flow pretty freely as we watch the pH meter increase. Already I've put in over 15 milliliters. We're at 2. I'm going to slow it down. Above 3 now. Okay, I hit 5. You can see that goes really quickly. It's up at 6. Basically just stopping the flow at this point, letting it equilibrate, and then if it needs more, I'll add drop by drop from here. Stable at 6.7, so I'll just add a drop, swirl it around, make sure it's reading new stuff. Oh yeah, that one drop took it over 7, so then we can come up here. We want to read our volume, so that's between the 24 and the 25, and I would say, a little hard to see on the screen, but that's 24.42 or so, somewhere between 24.4 and 24.5. Okay. So then in between runs, just want to rinse off our probe again with our deionized water. Make sure we write down the volume. 0.42 is what I think I read off of that. And then I need to refill the buret. Probably won't do that on camera again just because it's kind of a pain. But we'll go through one more titration on camera, and then I'll finish up the rest of this set off camera.
So my buret is full. Gotta bring it down to the 0 line. Okay. Bring in our next sample. Put the pH meter in. Read, and we can go off on our titration. Again, starting pretty quickly, and then slowing it down once we get to about pH 3. And if you're not comfortable with this, you can start with a slow flow, and you won't lose any accuracy. You'll just be spending a little bit more time doing it, and that's fine too. Sometimes as this is going, it can get hung up if it sticks on one pH for too long, so you do sometimes have to be watching that decimal point to make sure it's still flashing as it is. If it stops flashing, then the number won't change any, and you could be adding too much of your titrant before you know it. We're going to slow it down. Right about at 3. You can typically expect anywhere between 18 and 26 milliliters for these analyses, but there are always exceptions. If something has a particularly low calcium carbonate concentration, then it will take more of the titrant. Again, it's a little bit counterintuitive until you remember this is a back titration. We're actually titrating against the hydrochloric acid, which we use to react with the calcium carbonate. Alright, so we're past 7. I'm going to read that at, I would say 25 point, let's see when we get them into focus. 25.09 or so. It's not quite to the 25.1 mark. Okay.
That is the titration portion of our calcium carbonate analysis. I'm going to finish up the rest of this set off camera. And then we will go over to the data analysis part. So I finished with my last sample. All that's left to do at the titration station here is to clean up. So we just want to make sure we rinse down our funnel with the ionized water into our waste container, because that had sodium hydroxide going through it. We'll leave that to air dry. We want to rinse down our pH probe. I'm a little low on ionized water in this squirt bottle, but hopefully I can make it last. And then get that back into the storage solution, the probe. You don't have to do anything to the pH meter, it'll shut off on its own, but if you want, there's an on-off button. And then lastly, we'll need to drain the buret into the waste beaker, and then rinse that down with some deionized water as well. All of this, all of the samples that we've run, and the waste beaker, and our leftover sodium hydroxide, that should all be basic, and so we want to put all of that into our base waste when we're done.
Here we have our lime spreadsheet. You can find this on the J drive under limes, I believe. And the reason it is in a shared drive is that we have multiple departments working on this. If you take a look, we'll go left to right. We have our sample IDs, so obviously need those to make sure we're putting the data in for the correct samples. The next column is whether they came wet or dry. That's put in by the feed formulations team over on the other end of the hall. Then they are weighing it and putting it through a series of different mesh sieves and weighing the amount that goes into each portion. And with those weights, then they can figure out something about the particle size. So, you know, if all of the particles are very small, they will all sieve to the bottom, and you'll get a lot of weight very far down and not very much weight left on the 10. Whereas if the particle sizes are very large, you'll have a lot of weight left on the 10 and not much down here in the final weight. But it's good to know how that works in general, because it does relate to what we do. So if we scroll over, you can see it has this calculation for what gets reported from the particle size analysis, but over here is where we put in our titration values. One thing you might notice is that we have 2 empty columns right now for milliliters of sodium hydroxide. That's sort of an artifact of just an earlier time. This spreadsheet was built when we did this analysis in duplicate, but we have since transitioned to doing it only one time, or if a sample fails, we will come back and do it in duplicate. But so for now, to make the calculations work, we will have to fill in both of these columns, but we're just going to fill them in with the same value for each one. That actually has a little unexpected added bonus where it helps me check my data entry to make sure I did it right. So I'm just going to be quickly entering the data in that we got the other day. So for this first one, check to make sure, yeah, 08016, that was 24.35, 24.42, 25.09, 40.14, 37.50, 37.33, 36.56, 36.38, 21.19, 26.02, and 20.89. So, as I was doing this, you might have noticed that the values over here we're filling in. They may still need to update after going here because these are going to be taking averages from these two, and so it's averaging 24 and 0 because nothing's in there and giving us a value over 100%, which is not correct. So again, I'm just going to write down the values that we got: 24.35, 24.42, 25.09, 40.14, 37.50, 37.33, 36.56, 36.38, 21.19, 26.02, 20.89. Alright, and then I will take just a little bit of time to double check to make sure these two values match each other. Oh, so here's something. I had a little typo, you probably already noticed it. 24.42. Therein is the value of doing this. Okay, 25.09, 40.14, 37.50, 37.33, 36.56, 36.38, 21.19, 26.02, 20.89. Okay, so those are now in, and like a lot of our spreadsheets, the beauty in it is we put in the raw data and it will spit out our reported value. However, it's always good to know what this is doing, and so I will explain in a little bit how to calculate the CCE. Basically, it is taking this value and then multiplying it by the concentration of the sodium hydroxide and then subtracting that from the initial concentration of the hydrochloric acid, and that tells us how much calcium carbonate equivalent is in there. And then over here, this is just averaging the two CCE columns. So that's the value that we get directly from the titration, and then the final column is the RNV, the relative neutralizing value, and that's calculated using the CCE average, the calcium carbonate equivalent, and the sieve data. And so that's why this is all put into one spreadsheet, even though it crosses multiple departments, is this final value, which is probably the most important value to the customers, requires both of these pieces of data in order to calculate it.
So let's talk a little bit about what we did today. Now, if you watched the video on carbonate and bicarbonate in aqueous solutions, this should be pretty familiar. It's a similar analysis. In fact, we're looking for carbonate in both cases. However, in this case, it's in solids, and in the other one, it's in water. So we had our beaker filled with water and some calcium carbonate solid. We added hydrochloric acid into that in excess, right? So we have HCl, 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 some amount of hydrochloric acid in there, and crucially, a known amount, right? We knew we put exactly 50 milliliters in, and we know the concentration of that standardized hydrochloric acid to be, I believe it's exactly 0.5 normal. And so we know how much hydrochloric acid is in there. Well, in that solution, the hydrochloric acid and the calcium carbonate are going to react. I think we are going to need 2 of those guys. 2 hydrochloric acid molecules for every 1 calcium carbonate. The calcium and the chloride are going to get together and end up as just spectator ions. So we don't really care about those.
and then the hydrogen and the carbonate are going to come together to make carbonic acid. Interestingly, carbonic acid doesn't just stay in that form, and what we saw when we put the hydrochloric acid into our solution were a lot of bubbles forming in some of those, some more than others. And so what happens with the carbonic acid, H2CO3, that breaks down into carbon dioxide, CO2, and that's a gas, plus H2O, that's a liquid. So it's pretty simple. It's a lot simpler than our barium chloride precipitation for the carbonate and bicarbonate. You're basically just putting in a known amount of hydrochloric acid and then reacting that with the calcium carbonate in the solution. And then by taking how much of that reacts, we then go and titrate with sodium hydroxide. And so that is just our classic sodium hydroxide plus hydrochloric acid is going to neutralize and turn into sodium chloride plus water. And so that part is where we are titrating to a pH of 7. So we've done this, we put the hydrochloric acid in, reacted it with the calcium chloride, boiled it so that we make sure that reaction goes to completion. All of the calcium carbonate, excuse me, I think I said chloride before, all of the calcium carbonate is reacted away. There's still some hydrochloric acid left, so like, you know, it's 2 HCl's to 1 calcium carbonate. In this very pared down version, we'll say these two go in and react with that 1 calcium carbonate. Well, there's still that hydrochloric acid remaining, and so that's what we react with this sodium hydroxide here, and we're measuring how much sodium hydroxide we're putting in. We know the concentration of that sodium hydroxide, and so from that we can determine how much hydrochloric acid was left in solution after it had already reacted with the calcium carbonate. And so again, this is a back titration. We're titrating to see what was left after a different reaction happened, and then subtracting backwards to determine how much of the original thing we care about was actually in there. So that was the chemistry, but there's a little bit more, a few more pieces to this puzzle that we do. What I described and what I showed you today is how we determine the CCE, which is our calcium carbonate equivalent. And it's called that because it doesn't necessarily have to be calcium carbonate. It could be sodium carbonate, it could be magnesium carbonate, whatever. It's the carbonate we care about, or something that will act like carbonate in the soil, i.e. something that will bring the pH up and counteract some acidity that's in your soil. That tells you how much is in your product, but that's not as useful of a value to farmers who are going to use this product as the R&V. So that is our relative neutralizing value. The R&V is related to the CCE in that you use the CCE to calculate the R&V, but there's another portion that goes into the R&V. It's not something that I personally do. Currently, Zane does it. Maybe by the time someone in the far-flung future watches this, it'll be somebody else. But we also test for the particle size on our lime samples. And so if you think about it, if you have some chunk that has a known concentration of calcium carbonate, this big old chunk, or you had that same mass but broken into smaller amounts, this is going to be more available to the soil than that, right? This is only going to react on the surface of it, and then this part in the middle is not going to really have much of an effect on the soil. Same thing over here, it's reacting on the surface, but with finer particles you have more surface area. And so the RNV is a calculation that takes that into account. Over on the other end of the hall, they'll pass this through a series of sieves, and it takes into account the percentage that gets through a mesh 10 sieve, which is a fairly large sieve, and then the percentage that gets through a mesh 50 sieve. It averages those two together and then multiplies it by the CCE. And so you could have, for instance, a very high CCE value, but if your particle sizes are too large, then you're not going to get a lot getting through those sieves, and you're going to be multiplying by a small fraction and get a lower number. You could instead potentially get a better RNV by having a lower concentration of calcium carbonate equivalent, as long as you have a fine enough particle size. Now, ideally, if you want, the most bang for your buck as a farmer, you're going to have something with a high CCE and a very small particle size, giving you a high RNV.